Hello, my dear young friends. Welcome back to C Level Physics YouTube channel. Today, we are going to discuss projection of uniform circular motion as simple harmonic in nature. See, here we have one particle which is moving along circular path as shown in diagram. See here, clockwise sense. See the revolution of particle clockwise, right? So in XY plane, here particle is moving in circular path with constant speed in XY plane. Constant speed in the sense when speed of particle in a circular path is constant, then that is said to be uniform circular motion. So, see here, projection of uniform circular motion as simple harmonic in nature. Suppose here particle is moving in circular path in clockwise sense as an example. Okay. At t equal 0, this is the position of the particle. See the first situation, situation number 1. When particle lies at t equal to lies at positive y-axis at t equal to 0, and in some other instant at t equal to it reaches somewhere here, right? Now see the radius vector makes some angle like this, right? This is what radius vector. So radius vector, radius is a, for example. So at t equal to 0, this is the position of the particle. At t equal to this is the position of the particle. Now the radius vector makes an angle omega t. In this time interval t, it makes an angle omega t. It sweeps an angle omega t. So here I want to draw two normals onto x and y axis respectively. See here, this is what x axis. From the position of the particle, I drew one normal onto x and onto y also. So this intersection is said to be x projection on x axis. Now this intersection is said to be y projection on y axis. So these are nothing but projections, means the length of the foot. See, this is what length of the foot. This is also length of the foot for this position of the particle. So those are nothing but projections, x projection and y projection, right? So in a time interval t from 0 to t, this is the position. Therefore, it covers, it sweeps an angle omega t here, right? Now, during the revolution of particle along circular path in clockwise, now see from y axis to x axis. See from this position to this position, what happens? It moves along first quadrant like this. Along first quadrant. Now, if this is the position, y becomes from 0 to radius. So this is the ultimate projection from here to there. At t equal to 0, this is a projection, but during its motion along circular path in first quadrant, here what happens, as it moves like this projection decreases from peak to 0 value, means from peak to main position it decreases. See, in first quadrant like this, in first quadrant, during the motion of particle in first quadrant in clockwise, so y projection gradually decreases. Y projection gradually decreases like decreases, right? At the same time, x projection increases. When it is at t equal to 0, x becomes 0. Gradually it moves in first quadrant. What happens? X increases and becomes max. So x projection increases. So this is what motion of particle. During the motion of particle in first quadrant, y projection decreases and x projection increases, right? Now, during the motion of particle in the fourth quadrant like this, see, in fourth quadrant, what happens? Again, x decreases, x projection decreases and y projection increases. Okay. During the motion of particle in the third quadrant, what happens? Third quadrant like this. So in third quadrant, in clockwise, what happens? X increases, crossing main position, and x increases like that. At the same time, y decreases. Y decreases. So during motion of particle in second quadrant like this, in second quadrant like this, what happens? Again, x decreases and y increases. See, here particle completes its oscillation like this from here to there. So this is what one oscillation, one revolution of the particle is said to be completed. See, from here to there like that. This is what one revolution. Within that revolution, what happens here? projections, respective projections on x and y axis. See, this is what the oscillation projection, like this, like this, like this. This is also oscillation projection along y axis, like this, and like this. Okay. So within one revolution of the particle along circular path, here both x and y projections makes oscillations about fixed origin, that is what to and from motion. See, oscillation, what is the nature of oscillation here? To and from, x projection makes to and from motion, y projection also makes to and from motion. Here, what is the time period of the particle along circular path? The t equal to 2 pi by omega, that is what constant. Why? Because here the speed of the particle in circular path is constant. Why? Because that is uniform circular motion. As speed is constant, t equal to pi by omega also constant. So time period of the revolution of the particle is constant, implies that the time period of oscillation of projections also constant. So that means to say that here motion of projection repeats itself in regular intervals. So one condition is fulfilled. What is that condition? For any motion to become simple harmonic, the first condition, motion must be periodic, and second condition, it must be to and fro. See here, both x projections and y projections making oscillations about center, that's what is the nature? To and fro or back and forth. See, x oscillation, x projection makes to and fro motion, y projection also makes to and fro motion. So that's why here particle is not said to be under circular motion, simply that is under uniform circular motion. Particle is not making simple harmonic motion, but its projections, respective projections, that is x projection and y projection, making simple harmonic motion. Okay, so here particle is not at all moving simple harmonically, but its projection during the uniform circular motion of particle with constant speed, then its projections along x and y axis making simple harmonic oscillations. See here, y projection oscillates like that, x projection oscillates like that. See, during one revolution like that, here y decreases, x increases. In second quadrant, x decreases, y increases. In third quadrant, fourth quadrant, x decreases, y increases. In third quadrant, y decreases, x increases. In the second quadrant, x decreases, y increases. So within one revolution of particle along circular path with constant speed, so here its respect to projections making simple harmonic motions about center here, right? So that's why what I am saying means here uniform circular motion is nothing but the combination of two mutually perpendicular linear simple harmonic motions. So whenever particle moves with constant speed along circular path, that motion can be treated as the combination of two mutually perpendicular linear simple harmonic motions, right? Remember that here particle is not moving simple harmonically, but it respect the projections only making simple harmonic motions, right? Okay. Now here two options are there to have projections, x projection and y projection. When do we consider x projection? When do we consider y projection? Suppose here during the revolution of particle along circular path, if y dash is the reference axis, then x becomes projection. See, if this is the reference axis, we have to consider x projection. During the revolution of particle, we have to consider x projection like that. X projection about mean position O. Right? If x dash is the reference axis, then we have to consider projection along y axis like that. See, if x dash is the reference axis, we have to consider projection of y along y axis like that. See, this is the oscillation, simple harmonic oscillation. In previous case, this is the simple harmonic oscillation like that. Okay. So uniform circular motion is treated as the combination of two mutually perpendicular linear simple harmonic motions, right? So in first situation, see, at t equal to 0, this is the position of the particle. At some instant t equal to, this is the position. Now, what is the phase angle swept by the radius vector here omega t, right? Now for this situation, how can you write valid simple harmonic expression? Very simple here. See, by drawing normals from the position of the particle onto respect to x and y axis, we have to right angle triangles. I don't want to consider y, I want to consider x projection. Why? Because I took y o y dash as the reference axis. So this is the reference. So x is the projection. Now see, in this right angle triangle, sine if this is omega t, this one also omega t, all right angles. Therefore, sine omega t equal to opposite side by hypotenuse. So sine omega t equal to opposite side by hypotenuse, that is x by a. In fact, this is what radius of the circle, but that itself amplitude. So what is the maximum projection for x and y here? If x reaches here, so x becomes equal to radius. That itself, for its oscillation, it becomes amplitude. For projection y also, when particle reaches here, y becomes equal to radius. That itself amplitude. So in case of circular motion, uniform circular motion, radius of the circular path itself amplitude. So maximum displacement. So x equal to a sine omega t is the valid simple harmonic expression when particle initially at the position of y-axis, and in some other instant, if this is the position of the part, that is particle lies in first quadrant in some other instant. So x equal a sine omega t is the valid expression. Suppose for a equal to 5 centimeter, t equal to 4 second. Now expression can be written as x equal to 5 sine 2 pi by capital T means 4 into t like that. That is 5 sine pi by 4 t. So this is the expression, right? Now coming to second situation. What is the second situation here? Suppose particle lies in first quadrant initially. First quadrant. Say this is the position of the particle, t equal 0, right? So it has some initial phase already. When t equal 0, already it has some initial phase pi with respect to reference axis y dash. So at some other instant t equal to t, let this position be, this is the position of the particle. See, at t equal to 0, this is the position. At some instant t equal to, this is the position of the particle, right? So within the time interval, what is the phase angle here? Omega t. This is what amplitude A. Radius itself amplitude. Now try to draw normal onto x-axis here. X-axis. So with respect to reference axis, see, try to draw one more normal onto y-axis also like that. Y-axis. Now what is the total angle made by radius vector with y-axis means pi plus omega t. Pi plus omega t. If I consider this right angle triangle, now what happens? This is what x projection. So as y-axis is the reference axis, we have to consider x projection. So therefore, from right angle triangle here, sine, see this right angle triangle. What is the total angle here from here to there? That is pi plus omega t. That is omega t plus pi. So sine of omega t plus pi equal to opposite side by hypotenuse. What is opposite here? X. So x by hypotenuse means what? Amplitude, otherwise radius. So x equal to a sine omega t plus pi. This is the valid expression for this situation. What is that situation? If particle lies in second quadrant itself at initial instant and later instant, then what is the valid expression? X equal to a sine omega t plus pi is the valid expression. Now third situation. Suppose at t equal to 0, This is the position of the particle. So I want to rub the written matter. See here. Third situation. What is that situation? Initially particle lies somewhere here. See, I want to complete the circle here. Right? So at t equal to 0, this is the position of the particle. What is the initial phase here? Pi by 2. Already with reference to y over y dash, it has some initial phase pi by 2. Why? Because at t equal to 0, this is the position. So with respect to this axis, already it has initial phase pi by 2. At some other instant, it reaches the position somewhere here. So at t equal to t. Now in the time interval, what is the phase angle acquired here? Omega t. Omega t. Now what is this amplitude A? Now what is the valid expression here? X equal to A sin. X equal to A sin. See, valid expression here. X equal to. See, I want to draw a normal onto x axis. So this is what x. So x equal to valid expression here. X equal to. See here. A sine of what is the total phase angle by that instant when it reaches this position. See, pi by 2 plus omega t. That is omega t plus pi by 2 with respect to axis. So omega t plus pi by 2. Omega t plus pi by 2. That is an extension. What is omega t plus pi by 2? That is x equal to a sine sine 90 plus theta, that is cos theta. So a cos theta. A cos theta. Theta means what? Omega t. That is a cos 2 pi by capital T into small t also. So this is the valid expression. When it is valid here, the situation in which particle initially lies on positive x-axis and some other instant it lies in fourth quadrant, right? So in that situation, x equal to a sine omega t plus pi by 2 is the total phase. Now what is the initial phase here? Replace t by putting 0 to get initial phase. So when t equal to 0, we left with pi by 2 only. So when t equal to 0, this is the phase angle pi by 2, right? Okay. Now fourth situation. What is the fourth situation here? Suppose this is what initial position of the particle at t equal to 0, for example. Okay. Now at some other instant t, let this position be the position of the particle. Now this is what at t equal to t. Now see, at initial instant and some other later instant, particle lies in fourth quadrant itself. Now what is the valid expression? If you want to write a valid expression, see here at this position, what is the x projection here? Try to draw normal from the position of the particle onto x-axis like this. See, this is what? Amplitude A. So this is also amplitude A, right? So this is what x projection. Now what is the valid condition here? X equal to a sine of what is the total phase on reaching this position? What is the total phase? Means what is the total angle made by radius vector with respect to positive axis? See, this is what pi by 2 plus this is what initial phase, some phase. This is what omega t. From here to there, time elapsed is t. That is phase angle acquired from here to there. That is omega t. Now what is this angle here? This is what x. What is this angle here? Some pi. Okay. So from here to there pi. From here to there omega t. From here to there pi by 2. So what is the ultimate angle here? Phase angle pi by 2 plus pi plus omega t. So therefore sine of total phase omega t plus pi plus pi by 2. Pi plus pi by 2. Now see, I am coupling these two terms omega t plus pi by 2. So sine of 90 plus theta, sin 90 plus theta, that is cos theta. So therefore x equal to a cos of cos theta. Theta means instead of theta omega t plus pi is there. So sin 90 plus theta equals cos theta, that is cos of omega t plus pi. So this is the valid equation. When part lies initial and at the later instant in the fourth quadrant itself, our formula is valid formula for SHM is x equal to a cos omega t plus pi. Right? Now fourth situation. Fourth situation number 4. Suppose at t equal to 0, part is somewhere here at negative extreme position on the y-axis. So I want to rub the same diagram. See, this is what y dash at t equal to 0. This is the position of the particle. Alright? At some other instant t, at t equal to t, this is the position of the particle. Now what is the time elapsed from here to there? Means between these two instants, time interval is t minus 0, that is t. So in that time, radius vector makes an angle, this is what a, omega t. Now from here to there, what is the ultimate angle here? That is pi by 2 plus pi by 2. So what is this total angle from here to there? That is pi. 90 plus 90, that is pi. So total phase angle with respect to y-axis, positive axis, that is pi plus omega t. Pi plus omega t is the total phase angle. So x equal to a sin pi plus, see here pi plus omega t, that is omega t plus pi is the total phase. So sin of total phase, pi plus omega t, that is omega t plus pi. When t equal to 0, means when t equal to 0 somewhere here, when particle lies somewhere here at t equal to 0, what is the initial phase with respect to positive axis? That is pi. So when t equal to, I'm putting t equal to 0, we will have pi on. So pi becomes initial phase, right? So that is x equal to a sin omega t plus pi, implies that ultimately we can write sin 180 plus theta, that is minus sin theta, that is minus a sin omega t. Sin 180 plus theta means minus sin theta. Theta means what? Omega t. So this is the required or valid expression for this situation. What is that situation? Initially particle lies on negative y-axis. Later on, it lies in the third quadrant at some other instant t. So in that condition, we have to consider x equal to minus a sin omega t. Now situation number 5. Situation number 5. See here. This is what initial instant. For example, t equal to 0. This is the position of the particle. At some other instant t, at t equal to t, this is the position of the particle. Right? So what is the time interval from between these two instants? That is t minus 0, t. So in that t, what is the phase acquired by the radius vector or amplitude here? That is omega t. Now this is what, say some pi. So from here to there pi plus here to there pi plus here to there omega t. Now what is the total phase angle made by the radius vector, otherwise amplitude vector, with respect to positive axis, means pi plus omega t. So we have to replace the general expression, that is omega t plus pi, omega t plus total phase, omega t plus pi is the total phase. Now see, on coupling these two terms, this is in the form of sin of pi plus theta, that is minus sin theta. So x equal implies x equal ultimately it can be written as x equal to minus a sin of theta. Theta means what? Omega t plus pi. This is the valid expression for this situation. What is that situation? Arc lies initial and some other later instant in third quadrant. So like this. See, clockwise sense of revolution of the particle. So this is the valid expression. Now situation number 6. Sixth situation, that is initially particle is at negative x-axis. Later on it reaches at t equal to second quadrant, for example. Second quadrant, this is what A. Now I want to rub the previous written matter, right? So from here to there, as usual, pi only. From here to there, that is what? Some initial phase pi. Now between 0 and t. Now what is the phase angle required here? That is omega t. Sorry, not this one. Sorry. So this is the initial instant. Therefore, we have to consider total angle up to here. So up to here. That is from positive axis up to at that instant, initial instant. What is the total phase here? That is 180, 90 plus 90 plus 90. That is 270 degrees. 270 degrees. That is 3 pi by 2. 3 pi by 2. Right? From here to there, omega t. Why? Because this is the time interval of t. In the t, it requires a phase angle of omega t. Omega t. This is what? Phase angle omega t. This is main question. Now, what is the total phase angle required by the radius vector or amplitude vector with respect to positive axis? 270 plus omega t. So, sine of omega t plus 270. Omega t plus 270 with respect to positive axis. See, initially this is the vector. Later on, this radius vector rotates like that. During the revolution of the particle, radius vector rotates like that. Right? But our initial instant starts here and next here. So therefore, we have to consider the previous phase angle also, initial phase angle also with respect to positive axis. So therefore, 270 plus omega t. That is omega t plus 270. That is sin omega t plus 270 equal to minus cos omega t. Minus cos omega t. Minus a cos omega t. This is the required or valid simple harmonic expression for that situation. Right? Sixth situation. That is initially at negative axis, x-axis, later on in second quadrant. Right? Now situation number 7. Seventh situation. Suppose this is the initial instant, t equal 0. Now afterwards at some t equal t, this is the final situation, final instant, right? Okay. Now what is the time interval between these two? That is omega t. Therefore phase angle required is omega t. Now this is what some phase pi here, some phase pi with respect to x-axis. So initially this is the radius vector during the revolution of the particle, but our clock starts here and triggers some area. Therefore during the revolution of the particle like this, this is the rotation of the radius vector like this. So like this, okay, like this. Now what is that ultimate total phase angle here by this instant when it reaches this position? That is 270 plus pi plus omega t. So x equal to some a sin omega t plus pi plus 270. So omega t plus pi plus 270. That is on coupling these two, we will have sin 270 plus theta, that is minus cos theta, that is omega t plus pi. Omega t plus pi. So this is the valid equation for this situation. Okay, right? So I want to give one sum. I don't want to solve it. Try yourself, friends. Try to drop your answer or solution in the comment box, right? So what is this, that the situation here? Say, suppose, see the question. In SHM, if x equal to plus root 3 by 2a is the initial position of the particle, initial position of the particle, and it moves in negative x direction, write its simple harmonic equation. Here A means amplitude of oscillation. See here, in SHM, if x equal to plus root 3 by 2a is the initial position of the particle and it moves in negative x direction, write its simple harmonic equation by taking a as the amplitude. Okay friends, try to solve it. If you get your answer, you can drop in the comment box. Okay friends, bye.